the series. So in this video lecture, we'll be implementing this trie data structure. So before you watch this video, make sure to watch the previous video because I have implemented the same data structure using pointers. In this video lecture, we'll be implementing this data structure using 2D arrays. So let's see how we can do that. So let's say we have this dictionary which contains these 6 words. The range of the characters in these words is from small a to small z. That means we have at most 26 type of characters for every node to store. So let's build the corresponding trie for this given bunch of words. We start from this root node. From this root node we have the very first character for the very first word we are trying to store, that is trie, T-R-Y. So we store T here. From T we have another character which is R. From R we have Y. So in this fashion we store this word trie in this trie data structure, and we mark this character Y to be is and. So its is and boolean variable is marked to be true. That is, here we mark the end of this word which starts from T and ends at Y. Let's try to insert car. So do we have a child for the root node which contains C? No. So we create a child which contains C, then we create a child which contains A, finally we create a child which contains R. And here at R we mark the ending of this word. Okay, so we have stored car word in this trie. Let's store this word cat. So we start from C, then from C we move to A, then from A. So let's store this word cat. So let's check if we have CA in this trie. So we have C here, which is the very first child of the root. Then we also have A as a child of C. Now, do we have a child T for node A? We do not have T as a child of node A. So we create a child for node A and we store T there. Now, we try to insert this word TRIE into this trie. So let's start with the T. So we have T as a child of root. Now from T we have R as the child. Do we have I as a child? No. So we create I as a child of node R. Now from I we create E as its child. So now we have stored trie here. Let's store cards. Do we have C as a child node for root? Yes, we have C. Do we have A? Yes. We have A as a child node for C. Do we have R as the child node for C? For A, yes, we have R as the child node for node A. So let's store D as the child node for character R. Let's store S as the child node for a character D, and we mark here as the ending character. S is the ending character here, T is the ending character here, E is the ending character. So the boolean variables or the boolean is and variable for these characters are marked to be true. For other characters they are marked to be false. Let's store A and D. Do we have A as the child of root? No. So we create a child A and we make it as a child for root node. Now, do we have n as a child of A? No. So we create another node and store n there. Do we have D as a child of n? No. So we create another node and we store D there, and we mark this D to be the ending character for this word which starts at A and ends at D. So in this fashion we have builded the trie corresponding to this dictionary of words. Let's see how we can implement this using 2D arrays. So in the previous video we have implemented the tries using pointers in C++. So in this video we'll be implementing these tries using 2D arrays only. Let's see how we can do that. So first of all, let's just count how many words, how many nodes we require to store these words. That depends on the number of characters we are storing, or the longest path in this trie, which is this one. Okay, because that will give me the maximum number of nodes which I require. So in this path we have 1, 2, 3, 4, 5 nodes correspond to the length of this word cards. So That means we require at most 5 nodes to store our trie. So n is equals to 5. While for every node we require an array of data, an array of size 26 to store these 26 characters, because the range of the characters in these words is from small a to small z. If the range would have been different, then we would have taken a different array whose size may be different from this 26. Since we just contain lowercase English letters, we take an array of size 26. So let's implement it. Let's see the typical node structure. So all we have to do, we we need to know these two things, that is maximum number of nodes required, and for every node how many characters we need to store, or there are possibilities to store. After that we just create an array, a 2D array of dimensions n cross 26. Okay, so here n is 5, so let's create an array of dimensions 5 cross 36. Okay, 5 cross 26. That would be like this: 0, 1, 2, 3, 4. And for so these numbers represents the nodes. So this is node number 0, this is node number 1, node number 2, node number 3, and node number 4. So if we have n nodes, they will be numbered from 0 to n minus 1. Now for every node we have 26 characters which we can store. So that's why we take an array of size 26 for every node. So in this fashion we have a kind of adjacency list, or a 2D array we can say, and we have 26 slots for every node, starting from node number 0 till node number n minus 1. So here the very first slot is corresponds to the character A. This corresponds to the character B, C, D, E, and so on. Although the actual indices are 0, 1, 2, 3, and so on. Like A corresponds to 0, B corresponds to 1, C corresponds to 2. Fine. So let's try to store the words in this type of trie. So we had the dictionary that we had, the very first word was T-R-Y. Okay, so A, B, C, D, E, F, G, H, I, J. So we had somewhere T here. Now from that T, so let's say we have like, so for the slot, so let's say we have T somewhere after a couple of nodes, we have T here. And what do we do to store this node trie? We iterate, we go to the very first node, start from node number 0. So we start from node number 0, and for this node number 0 we want to store this T. So we go to node number 0 and we come to this slot, and here we simply put 1. So what I'm saying here, okay, so this is the very first character which I have encountered for this word. I want to store this word try. Go to the node number 1 to look for this second character. That's what I'm saying here. Okay, so that's why I store 1 here. And now I move to this node, because this character T is directing us to this node, that is node number 1. So I come to this node, which is node number 1, and here I'm searching for R. So corresponding to R we have some slot like over here corresponding to node R. So here we store 2. That is what I am saying is, okay, we have found T, we have found R. Now we have inserted T, we have inserted R. Now to insert Y, so remember I'm explaining insert operation here, how we're gonna build the trie. So to insert Y, go to the node number 2. So we move to this node, that is node number 2. And here corresponding to slot Y, what I'm gonna put is, so this is Y, so this is Y. So corresponding to node y, I'm going to store 3. That is, if you want to look for the next character, then go to the node number 3. But here we do not have to go to this node, because here we are simply marking this character y as the ending character for this word. How do we do that? To do so, we use an extra array. Let's call it is and array. So we also take another array. This is and array. And in this array, this array has a size of n. It has a size of n. So 0, 1, 2, 3, 4, and so on. Now, since this node, which is node number 2 here, is the ending node, what I'm going to do is I'm going to mark this node as the ending node. Okay, so since this character here at this character, which is character y, corresponding to this character y, we have like node number 3. That means for node number 3, we store 1, or we store t. T stands for true. That is, this node, node number 3, is the ending node for this word. Fine. So in this fashion, I basically store a word in a trie using 2D arrays. Let's store the next word, which is car, C-A-R. I want to store this word. So let's start from the very first node. To do so, we'll start from the very first node, that is node number 0. So since I want to store car, for this node, for this character C, I will start from node number 0. So which is this one. So for this node, move to the slot which contains this character C, that is which like corresponds to this character C here, and store 1 here. So what I'm saying, okay, I have inserted character C at node number 0. Now to insert the next character, which is A, move to this node, which is node number 1. So I move to this node, and at this node I store A. So I put 2 here. So what I'm saying, I have inserted A at node number 1. To insert the next character, which is R, move to node number 2. So I move to node number 2 here. So at node number 2, we want to store this R. So corresponding to this R, we have slot here, and here I put 3. That is, I have inserted R in this slot corresponds to node number 2. To store the next character, move to node number 3. But here, what I noticed that R is the last character of this word. I'm done with the characters. So I have inserted all of the characters of the word into the trie. That means for node number 3, I'm going to mark true, which is already marked true here. So in this fashion, I'm going to insert the words into the trie. So let's see how we can search for a word in the trie. So let's say I want to search for, again, let's say I want to search for Try. Try. So to do so, I will again start from node 0. So I initialize this node variable to 0. So I start from this node, which is node number 0. And at this node, I move to the slot corresponding to the character number T here. It contains 1. That is, okay, I have found T. Move to the node 1 to look for the next character, which is R. So I move to the node number 1. And at node number 1, I want to look for R. So move to the slot corresponding to character R, which is this one. So what I'm saying, okay, I have found R here. To check for the next character, move to the node number 2. So I am here at node number 2. And at node number 2, I come to the slot corresponding to this character Y, which contains 3. That is, I have found Y. To search for the next character of the word, move to the node number 3. But what I see, I am done with my word which I want to insert. I want to check whether Y is the last character, or if it was inserted, then that means Y must be marked true. The node corresponding to Y must be marked true. So I check here in this array. I can see that the node which is 3 corresponding to character Y is marked true. That means trie was inserted, and hence it is present in the trie. So we return true in this case. That's how I search for a word. Let's say I want to search for a prefix. If there is a word which contains a prefix, let's say CA. Okay, to do so, I will again start from node 0. So start from node 0, come to the very first character C, and corresponding to this character C, find the slot here in this node number 0, which is this one, and it contains a non-zero value. All other slots contains 0 value except C and T. So this C contains 1. That means, okay, I have found C. To check for the next character A, move to node number 1. So I come to node number 1, and here I want to check for A. Now check for A, which is this one. Okay, I do not, okay, I didn't inserted, okay, I didn't inserted A here. I think this was a mistake. So this, okay, so this is not D. So this is D basically. So this I inserted car, C-A-R. That means corresponding to character A, we must have 2 here. So this is wrong. Okay, so I come to A and I see, okay, I have found A. We have a non-zero value here. That means I have found A. Move to the node number 2 to check for the next character. But I am done with traversing my prefix which I wanted to search. That means I have found both of the characters into the trie, and hence that simply means there there is at least one word, which has a which has CA as its prefix, which starts with this CA, and hence we return true in this case. So that's how the starts with functionality works in this implementation. Let's jump to the code implementation part. So so this is my try class. In this try class, I want to implement the code for the try using 2D arrays. So let's first declare those arrays. Let's declare a 2D array, the try array, corresponding to the matrix which I explained in the slide. TRIE of dimensions, let's take 2 0 0 0 0 2, and every node. So this I'm putting a upper bound here. That means take any test case in this problem statement. Look at the constraints. Any test case will never cross, like, and the maximum number of nodes in any test case will never exceed this number. Now for every node I have 26 characters to store, because notice that we have just lowercase English letters and we have 26 lowercase English letters. Now we also need a boolean array, that is and array, to mark the ending of a word which we have inserted. It has a size same as the number of nodes. So again put an upper bound here, and apart from it also declare a node, current node, to, or let's say root node. Let's not call it current, let's call it root. So this is the node from where we have to start. Remember, whenever we initialize a node with 0, that means we are starting from this root node. Okay, so let's jump to this public part, and here we can see that in this constructor what we're gonna do is we're gonna initialize. We also have to keep track of another variable, let's call it counter. And the purpose of this counter is simply, like, here I just, whenever I I wanted to insert this T at this position, and that's why I inserted 1 here. That is, okay, T is present. To check for the next character, move to node number 1. So to store this 1 2, I use this counter variable. Okay, and here in this try, what I'm gonna do is I'm simply initializing these arrays. So initialize root with 0, initialize try, like you can also do it like this. Do not initialize them here. Initialize these variables right here. Try initialize, like counter, initialize counter with 0, and also initialize these try array with 0, and this is an array with false. Fine. Now here into this, let's just jump to the, let's just implement this insert function. To do so, let's declare a pointer. Let's call it node. So this is the node from where we are starting. Since we start from the root node, we initialize it with the root node. Now iterate over the word. For every character, check if it is present or not. So in the try, if this character is present, c minus a, then this value try node c minus a is non-zero. So if it is 0, if it is null, then that means, or if it is 0, then that means we do not have this character at this node. We do not have character c at this node, and hence we store it. Try node c minus a. To store it, we just increment our counter with 1 and put it here. Why? What I'm saying, okay, at this node, corresponding, like at this node, I'm storing this character c, and it is saying, okay, we have this character here. To check for the next character of the word, move to this position. Okay, that's what I'm saying here. Now move our node to this position which we have stored here, node c minus a. Fine. And at the end, when we are done with traversing the word, mark the ending character of the word to be true. So is end, for the last node, mark it to be true. So that's how we insert the word into the try. Let's see how we can search it. Again, initialize the node with the root node, iterate over the word, check if the current word, if the current character is there, c minus a. If it is 0, then that means this character is not there. If it is the case, then return false right from here. Otherwise, move to the next node to which this current node is directing us to. Trie node c minus a. Fine. At the end, check if that means if I have traversed this loop, then that means I am standing at the last node, and check if the last node is the ending node, if it is marked as the ending node or not. So return is end node. So if it is marked true, then we return true, otherwise we return false. Let's see if we have a word in the try which has the prefix same as this prefix which has been passed in this function. To do so, again, initialize this node with the root. We start from the root node, iterate over the prefix. So c prefix, check if we have this character in the try. So if we do not have this character, then just return false right from here. Otherwise, move to the next node to which this node is directing us to. And at the end, return true, because we have found a prefix which, like, there is at least one word which starts with this prefix. Fine. So that's all we have to do. That's how we implement try using arrays only. Although it consumes a little bit more memory than the previous implementation, but we do not use pointers here. Okay, it's accepted. Let's submit it. Accepted. So let's jump to the complexity part. Let's analyze the complexity here. You can see that the time complexity stays the same as we are just iterating over the words in these functions. So let's say if we have a word of size k which we want to search, insert, or check if it is a prefix, then we require big of k time complexity. While the space complexity is again n into 26, where n represents the number of nodes, the maximum number of nodes which we have, or n corresponds to, what is n here? N corresponds to max characters. So let's write it over here. So here the complexity is the space complexity is n into 26, where n represents the maximum number of characters which a word may have, which a word has. So we simply take the longest word, and the length of that longest word represents this n, and that's my space complexity. Although we also use arrays like is and array, so n, the overall space complexity would be n plus 26 plus n. That will give me big of n. Fine, so that's all, and I hope you got what we did in this video, and this is just another implementation for the tries, and I hope you enjoyed it. And in the upcoming videos, we'll be solving problems over this data structure. So stay tuned with me, and I hope to see